In this lesson, we will present the high-level elements required in the Intelligent Transportation Systems or ITS space, describe high-level components of connected fleet and rail, list ITS standards and protocols, identify IT requirements and explain IT considerations of availability, redundancy, and wireless connectivity for ITS. In this lesson, we will present an overview of the Intelligent Transportation Systems space. Intelligent Transportation System, ITS, describes the integrated application of communications, data managing and handling of industrial solutions for transportation systems. These systems are highly effective because they save time and energy consumption. In Europe, the term transport telematics is used to describe this class of transportation technologies. ITS can be applied to all varieties of transportation and takes into account how the elements of each system, such as a vehicle, the operator, and the infrastructure dynamically work together. It relies on information in order to be efficient. Information may be static or fluid, such as digital mapping or real-time traffic data. Most ITS devices collect, process, or integrate data in one way or another. This information is then used to make better informed decisions, such as changing routes due to traffic or maintenance delays, and following digital map directions to unfamiliar destinations. There is global motivation to implement ITS in all facets of transportation, including rail, roadways, public safety, aviation, maritime, mass transit, fleet and logistics, and vehicle-to-vehicle or vehicle-to-infrastructure V2X technologies. Some ITS benefits include relieving congestion by observing and predicting traffic conditions, coordinating and prioritizing traffic signal to minimize delay and make way for emergency vehicles, detecting and controlling traffic incidents, enforcing regulations by regulating toll charges, monitoring vehicle restriction areas, and utilizing cameras for traffic signal and speed enforcement, increasing safety and limiting environmental hazards by detecting pollution, cooperative vehicle highway systems, CVHS, promoting public transportation by offering flexible ticketing and cash-free travel options, providing accurate departure and arrival information, allowing public transportation to take priority for speedier journey times. ITS is broken into 8 segments that focus on the following user services. Electronic payment systems focuses on offering cash-free options in ticketing, toll collection, and parking infrastructures. Emergency management reduces the time it takes for emergency responders to arrive by automatically transmitting emergency notifications and security warnings. Maintenance and construction management manages fleets of maintenance vehicles to minimize incident and delay due to weather conditions, road constructions, and maintenance efforts. Information management enables the ability to collect and archive the large amounts of ITS-generated data. Advanced vehicle control and safety systems aim to enhance transportation safety through the use of collision warning systems, adaptive cruise controls, passenger safety systems, and automated vehicle operations. Commercial vehicle operations focuses on improving the safety and efficiency of commercial vehicle operations through services such as electronic vehicle clearance, automated roadside inspections, and electronic weight stations missions. Travel and traffic management collect traffic data and patterns to improve overall travel performance. Public transportation operations encourages the use of public transportation by focusing on heightened transit security, more accurate travel data, and improved public transportation processes. Intelligent transportation systems require a combination of technologies that dynamically work together. Technologies used in ITS include the following: communications, used for pre-clearance, fleet management, emergency response, and real-time trip planning. Geographical location, used for satellite-based positioning and vehicle tracking and tracing. Geographical information systems, used to access transportation networks and services based on the traveler's current location. Data acquisition and exchanges, uses real-time data to detect travel delays and provide alternate route recommendations. Camera systems, used for identifying traffic violations and security breaches. Detection and classification, used for managing heavy traffic, traffic incidents, and safety and security compliance. In-vehicle systems, used for supplying travel information, controlling vehicle systems, and preventing collisions. Digital mapping, used for traffic management, traffic information, route guidance, and car parking management. In order for the many transportation modes and varieties of travelers to take advantage of ITS, the networks must be dynamically integrated to work together. Shown here is a high-level diagram of the ITS distribution network. The architecture of the system is broken into 4 subsystems. Field monitors security, commercial and rail operations, parking management and toll collections. Control centers manage current and historical traffic data, tolls and ticketing, maintenance, commercial and fleet travel, and emergency response. Vehicles consist of 5 types of vehicles: personal automobiles, public transit, commercial and fleet, maintenance and construction, and emergency. Travelers represent ways to access the system through portals, mobile devices, email, public broadcast, and in-car navigational systems. Each subsystem represents a combination of functions that enable intelligent travel decisions. Throughout the ITS distribution network, there are 4 communication types. Fixed point to fixed point, such as emergency management, for example, direct lines to first responders at a control center, or a traveler at a train station receiving travel support, such as scheduling information, arrival, departure, and status update displays. Wide area wireless, such as a traveler in a car accessing automated parking apps with a cell phone, or emergency personnel in an ambulance accessing patient information on a wireless device. Vehicles, such as travelers on a highway, warning each other about traffic delays, or public transport bus drivers, checking in with a dispatch center about current status and conditions. Dedicated short range, such as weigh-in motion sensors that collect information about weight on fleet trucks, or video surveillance security systems on board a train. These communication systems allow the subsystems to be interconnected, which enables data to be transferred and utilized dynamically. For example, traffic management is connected to communications to receive real-time rail and traffic information. The roadway subsystem uses traffic information to control traffic signals, detectors, and cameras. Let's take a look at some of the connected transportation solutions available today. Within the trucking and logistics industry, fleet operations utilize ITS to manage, control, and monitor fleet vehicles. According to ABI research, more than 12 million fleet vehicles hit the road every day in the US alone. Fleets support our global economy by reliably delivering products to local stores. When an enterprise's vehicle fleet is not effectively managed, business expenses not only increase, but there are also environmental and economic impacts, such as increased pollution levels and higher product costs. Companies with fleet operations have begun to implement more ITS technologies and connected fleet solutions for a more observable, automated, intelligent and transactive approach to managing vehicle fleets. Connected fleet. Through the use of intelligent networking and connected fleet solutions, fleet operators can monitor mileage and driving patterns to cut overall costs and reduce vehicle-produced carbon, limit vehicle theft by offering automatic engine shutdowns and vehicle tracking, increase emergency response time and automatically notify fleet managers in the event of a collision, streamline business operations through integrated fleet management software, help organizations comply with industrial regulations and government mandates. Railway transportation has much to gain from integrating ITS technologies. As an industry that is largely outdated, there are many disadvantages to overcome, such as high maintenance costs, aging support systems, and staff, as well as rising safety concerns. The use of intelligent devices in the rail sector has the potential to overcome these disadvantages. The connected rail companies encompass 3 foundational units. Connected train enables onboard passenger Wi-Fi access, real-time scheduling information, preventative maintenance, quick response security intervention, personalized entertainment. Connected trackside solutions enable accident prevention systems, digital signage, enhanced security video surveillance, trackside communication, and reliable train control systems. Connected stations enable passengers Wi-Fi access, smart automatic ticketing centers, customer information kiosks, and enhanced security and video surveillance. The ITS technology selected by the Railway Industry Association focuses on the following 4 priorities. Cost. Limiting operational costs for rail operators is the first challenge to overcome. ITS technologies that have been implemented to create efficiencies include automated and remote management systems, smart ticketing and passenger counting, intelligent train movement management. Carbon. An environmental push to cut down on carbon emissions is another focus of the Railway Industry Association. ITS technologies that have been implemented to reduce emissions from travel include parking guidance at railway stations, intelligent scheduling based on information collected by counting passengers. Capacity. One way to be cost-effective is to optimize train space by increasing the number of passengers without overcrowding. ITS technologies which can assist in maximizing capacity include intelligent ticketing that can be scanned from a smartphone, reliable passenger counting, supplying crowding information for journey planning purposes, and improved traffic management facilities, facilitating more trains on the track at any one time. Encouraging customers to travel by public rail is another priority of the Railway Industry Association. ITS technologies that can help rail travellers to plan their trips and travel safely and comfortably include displaying real-time information on the train at the platform, utilising mobile apps that track a customer's journey, providing delay information, providing infotainment using multimedia systems on the train and at the platform, installing security and surveillance systems on the train, at the station and in the car park areas, enhanced delay management and higher frequency of meeting timetables. On a connected railway system, the high-level architecture transportation system consists of the following elements. Onboard. The infrastructure on board a train is supported by a combination of high-speed wired and wireless networks and the use of mobile IP routers. The networks must be resilient to withstand continuous movement and train vibrations and must be robust enough to deliver a variety of connection services to both operators and passengers. Trackside. Access points installed along the track provide the trains with Wi-Fi connectivity. Since the APs reside outdoors, they are rugged and can withstand a variety of weather conditions and transportations. APs can also be used to connect nearby devices, such as surveillance cameras, to the transport network. APs are connected to the transport network through a wired connection using Cisco switches. Transport. A fixed mobile convergence is required to enable communication between the trackside network and the data center. In order for operators at the data center to monitor and control trackside and onboard devices, a resilient and redundant two-way communications network, known as the transport network, needs to be established. Data center. The data center contains a variety of application and data servers that allow operators to monitor, manage, and store data received from the transport network. Data is used to make travel predictions and make adjustments to onboard and trackside devices. For a connected rail station, Cisco Intelligent Station Architecture is an IP-based converged network that provides reliable communications for all transit operations, commuter information and security systems. The combined voice, video and data network provides quick and accurate passenger information while enabling fare collection, as well as security and facility management. An intelligent station also supports passenger services such as wireless connectivity in waiting areas. Cisco IP telephony. Cisco IP telephony is a key element of the intelligent station. Cisco IP telephony enables station operators to integrate applications such as schedules and directories through their phones. Wireless mobility. Cisco Intelligent Station utilizes a combination of wired and wireless networks to support all facets of transit, such as security, rail management, and the ability to support future growth. Data used to operate the system can be securely accessed from anywhere, including mobile devices, providing security personnel access to streaming surveillance, or allowing maintenance workers to access repair histories. Closed-circuit television or CCTV. Cisco Intelligent Station utilizes video cameras that are placed strategically around the station. Continuous video streams are monitored by security personnel in order to mitigate potentially hazardous situations and to identify and track suspicious activity. Several rail control systems used to enhance travel safety and efficiency are available as a result of ITS technologies. For example, Positive Train Control or PTC is a preventative collision avoidance system used in American railroads, used to monitor and control train movements for safety purposes. In Europe, similar systems such as Automatic Warning System and Train Protection and Warning System exist. PTC technology is designed to collect real-time data to predict collections and stop trains before an accident can occur. ITS technologies such as Global Positioning System and APs help advance PTC development. In 2008, Congress passed a Rail Safety Improvement Act that requires rail systems to implement PTC systems by the end of 2015. This requirement is intended to eliminate train collisions, high-speed derailments, and trains entering the wrong tracks. An effective PTC system is able to monitor the location and speed of trains in order to enhance safety measures already taken by the engineer. If an imminent collision is detected, warnings to slow or stop the train are activated. If warnings are ignored, the PTC will take control of the train, applying the brakes until the desired speed is achieved. Another rail system example is the European Railway Traffic Management System, or ERTMS. ERTMS focuses on rail interoperability between countries by creating standard control systems for all of Europe. Maritime transportation such as cargo ships, cruise liners and naval crafts also have much to gain from integrating ITS technologies into vessels and onto ports. Onboard communication is a struggle due to the harsh ocean conditions and the remote nature of sea travel. In order to become a more efficient industry, there are many disadvantages to overcome, such as keeping salt and moisture out of complex and expensive communication systems, staying on top of stringent onboard crew labour laws, tracking cargo shipments while at sea, and being able to communicate from far offshore. With the use of the following ITS technologies, maritime transportation can overcome some of the challenges at sea and in port. Automated port warehouses used in conjunction with interactive customer web portals allow customers to have instant access to ordering and status information. Sensors placed inside container units linked to communication antennas, providing real-time cargo tracking data. Rugged ITS devices and cabling are designed to withstand salt and moisture exposure. Crew and passenger management systems allow ship captains to track crew work and rest hours. Satellite communications enable long-range status updates, remote expert collaboration, and the ability to call for help if necessary. Ship-to-shore Wi-Fi communication systems provide mobile access to cruise ship passengers while in port, as well as providing logistics support to the captain and crew. IP cameras enhance port and vessel security measures. ITS technology has enabled airports to create a sustainable infrastructure. Connected airports around the globe support passenger services, airport security, facility management, navigational aids, baggage handling, and a variety of other air travel-related services. By utilizing ITS, Aviation is able to provide onboard passenger Wi-Fi and entertainment, minimize delays due to equipment failure with preventative maintenance, enable self-check-in and other interactive airport services, enhance security measures through IP cameras, limit lost luggage with cargo tracking and monitoring systems. Two key goals of mass transit are to help alleviate congestion and lower overall carbon emissions into the environment. However, many travellers who have the opportunity to use mass transit choose not to for a variety of reasons, such as safety concerns, crowded stations, or confusing processes. ITS technology can help increase mass transit usage by ensuring passenger safety and security through IP-based video surveillance, minimizing delays through the use of remote fleet and operations management systems, providing an enhanced ridership experience by offering an onboard passenger Wi-Fi, limiting breakdowns and delays with preventative maintenance and tracking, offering traveller services such as real-time mobile payment. Overall, all facets of transportation can benefit from ITS by making travel safer and more efficient. Some of the key benefits include limiting congestion, enhancing scheduling, enforcing regulations, enhancing operational and fuel efficiency, increasing traveller safety and limiting environmental hazards, making public transportation more convenient and enjoyable. In this lesson, we will explain how connected fleet and rail fit within the ITS space by presenting intelligent transportation system standards and protocols. To guarantee the safe travel in all facets of transportation, the following agencies focus on developing ITS infrastructure regulations and recommendations. The Department of Transportation is a US agency devoted to ensuring a fast, safe and efficient, accessible and convenient transportation system. The DOT proposes and enforces transportation regulations. Federal Railroad Administration is a US agency under the Department of Transportation. The FRA promulgates and enforces rail safety regulations, including those stipulated by the Positive Train Control Initiative. The American Railway Engineering and Maintenance of Way Association publishes railway design and infrastructure best practice recommendations for the US and Canada. And the European Commission of Mobility and Transport promotes safe transportation by the promulgation of policies and legislation and supporting initiatives like the European Rail Traffic Management System. As intelligent transportation systems become more popular, the need to develop ITS-specific standards and protocols becomes critical. ITS is already a widely used integrated system. Developing standards and protocols for ITS will help to support interoperability and compatibility between systems, minimize operational maintenance and future integration costs, facilitate regional integration, prevent technological obstacles, make procurement and system testing easier. Well-defined ITS standards determine how networks and devices interact by defining how data is transmitted, what type of media should be used, and what connection port standards are allowed. Two standards available today include EN 50121, a set of standards that describe requirements for railway applications, and EN 50155, a set of standards that describe requirements for electronic devices used on board. The EN 50121 standards describe requirements for railway applications. There are two parts that relate to ITS integration. Part 1, EN 50121-1, General Standards. Part 1 describes the railway environment and defines the management of electromagnetic capability between on-board devices and the infrastructure. Part 1 specifies performance criteria for EMC management within the infrastructure, such as static and mobile elements and trackside equipment. Part 4, EN 50121-4, Emission and Immunity of Signaling and Telecommunications Apparatus. Part 4 defines signaling and telecommunication device standards, emission limits, immunity levels, and measurement methods. Part 4 specifies performance criteria for signaling and telecommunication devices, emission and immunity limits. The railway standard EN 50155 applies to electronic control, regulation and protection devices on board rail vehicles that are associated with the vehicle's accumulatory battery, a low voltage power source with or without a direct connection to the contact system, for example a transformer, potentiometer device or auxiliary supply. This standard covers the conditions of operation, design, construction and testing of electronic equipment, as well as basic hardware and software requirements considered necessary for competent, reliable equipment. Intelligent transportation systems are implemented using a wide range of network components. However, devices connected to the network are typically connected through RS-232, RS-422 or RS-485 serial ports. Devices that require such ports include traffic signal controllers, camera controls, video encoders, decoders, loop detectors, ramp meters, queue detectors, variable message signs, lane control signals, pavement sensors, vehicle detectors, side scan radar, and smart tag readers. Modbus and TCP/IP protocols are also used to connect different devices to the control center. Electric trains often have small power substations called traction power substations along the trackway that supply railways, trams, or trolleybuses with power. Traction power substations align with utility-specific protocols such as IEC 61850, as well as other common industrial network protocols such as Modbus, TCP, and Profinet. In this lesson, we will present IT and considerations and applications for the ITS space. IT requirements for ITS include resiliency, rugged devices, high availability, and wireless access. In order to provide real-time data and ensure consistent operations, ITS networks need to be resilient. Most systems need to be operational 24 hours per day, therefore availability is a key requirement. ITS remote terminal units and remote input-output devices need to be rugged in order to provide reliable data in harsh environments and maintain availability. Control network security is an essential element of operational safety and efficiency, as well as ensuring overall passenger safety. Flexibility and mobility. Wireless connectivity is required to provide an unbroken connection to transit vehicles that travel from one connection area to the next. Remote access for management and tracking, as well as remote control of traffic signaling and rail switching devices. Components used within an ITS include industrial computers, located in control boxes or traffic centers, are ruggedly designed for harsh environments to provide reliable service. Sensors, implemented in an ITS, can be used to detect hazardous weather, heavy traffic conditions, and moving traffic violations. Cameras within transportation systems are used for law enforcement and security purposes. Cameras provide security to toll collection sites and parking decks. They are also used to capture speeding and traffic light violations, monitor traffic flow and detect delays caused by accidents or road maintenance. Remote terminal units and remote input-output modules collect real-time data that is used to notify travelers or control center operators of fluctuating conditions. ITS RTU and remote input-outputs are rugged in order to provide reliable data in harsh environments. In order to provide real-time data and ensure consistent operations, ITS networks need to be resilient. ITS systems span over long distances and many of the devices involved are outdoors, therefore are exposed to weather conditions. Taking those considerations into account, it is recommended that the ITS networks are configured into linear, ring, or layer 3 switching topologies. Networks that support multiple cell area zones may need to support multiple VLANs. In that case, a redundant layer 3 switching topology is recommended to run layer 3 switches and routers. Access layer switches typically function at the data link layer, or layer 2 of the OSI model. With layer 3 switching, there is an additional access layer of switches known as the distribution layer above the access layer. These switches interlink the various access layer switches. A variety of wireless communications technologies have been considered for intelligent transportation systems. UHF and VHF radio communications are often used for short and long-range communication. Short-range Wi-Fi communications, or more specifically WAVE, or the dedicated short-range communication standards, are recommended by the Intelligent Transportation Society of America and the United States Department of Transportation to establish communication between devices in close proximity. Longer-range WiMAX, Global System for Mobile Communications, 3G or 4G communications have been proposed using already existing networks. WLAN parameters can be configured to support a variety of applications. WLANs that perform in a controlled indoor environment will have a different set of parameters than those exposed to the outside elements. The parameters such as the beacon frame interval, short interframe space, DCF interframe space, and contention window size are specific to the general purpose use of WLAN. While these parameters are important for ITS-related communication, the signal strength and data rate need to be far more robust along railway tracks, roads and highways. Unique ITS requirements for WLAN. WLAN adapters, access points and mobile adapters must be able to operate in a more rugged outdoor transit environment. Multiple access points may be required to extend coverage areas across a transit system. Roaming WLAN access points are often required to provide an unbroken connection to transit vehicles that travel from one connection area to the next. Fast roaming WLAN networks are often used in ITS in order to quickly connect and transmit data between devices that do not stay in one place. On-vehicle devices, for instance, travel with the vehicle and therefore need to connect with stationary receivers quickly before they are out of range. The use of a fast roaming WLAN makes these connections possible. Some benefits of using this solution include the following: providing WLAN coverage in areas without public 3G or 4G connectivity, such as in tunnels or underground; supporting a highly available and redundant network; offering privacy and security of data. The use of wireless communication in intelligent transportation systems is redefining the way information is distributed. The cellular network, an infrastructure that already exists in many locations, can be used by ITS devices for a variety of applications. Handheld devices such as smartphones or tablets utilize cellular networks to access navigation information and traffic status updates. GPS units access cellular networks to provide navigation and journey planning services. Public safety vehicles receive dispatch communications in real time, allowing them to respond faster to traffic incidents. For devices that are not able to access cellular service, mobile hotspots can be used to provide wireless functionality. Using a mobile hotspot, passengers can connect their laptops to Wi-Fi. Security cameras on trains and buses can wirelessly transmit video packets. In addition, the data extracted from cellular networks can be used to obtain accurate road traffic information. In this way, the cellular networks not only distribute road traffic information, but they become the source of it. Some ITS networks require modern camera technologies that can monitor traffic flows and toll collection sites and can detect moving traffic violations. IP cameras are also used for security applications in mass transit stations and onboard buses and rail cars. IP surveillance solutions are easy to deploy over Ethernet. They are available in a variety of camera types with different physical profiles, such as a box or dome, and with varying definition capabilities, such as standard definition and high definition. Some benefits of high-IP surveillance include access to video at any time from any place, embedded security and networking, motion detection and event notification, automatic event detection such as unintended objects, crowding, tailgating, and so on through image processing algorithms in edge video analytics. IP surveillance supports a variety of functions within the ITS space. Some examples include the following use cases. Travel time and speed. IP surveillance enables the measurement of travel time and speed, which is used to detect traffic congestion. The data collected can be monitored and categorized as recurring congestion, caused by peak driving times, or incidental congestion caused by road construction or accidents. Incident verification. IP surveillance is used to verify incidents as they take place. Images taken at a detected incident site can be used to pinpoint the details of an incident, enabling incident mitigation teams to see the scale of an incident in order to dispatch the appropriate responders such as a fire truck or an ambulance or a hazmat team. Volume. IP surveillance measures the volume of people using public transportation. Volume data is used to predict overload times and allows transit operators to adjust the systems accordingly. Safety. IP surveillance can quickly and efficiently identify travelers who need assistance due to collisions or breakdowns on the road, and robbery and harassment on board mass transit rail or bus systems. IP surveillance is also used to identify vehicles that emit excess pollutants. IP surveillance helps to decrease roadway damage caused by overloading commercial trucks. Cameras are used with weight detection systems such as weigh in motion to enforce weight limitation regulations. Passenger occupancy. IP surveillance can be used to detect the number of occupants inside a vehicle to verify vehicle access to higher occupancy vehicle lanes. In this module, we have seen that there is global motivation to implement ITS in all facets of transportation. ITS covers all modes of transport and considers all elements of the transportation system, the vehicle, the infrastructure, and the driver or user, and dynamically interacting. Intelligent transportation systems vary in technologies apply from basic management systems such as car navigation, traffic signal control systems, variable message signs, or speed cameras to monitoring applications such as security CCTV systems. Railway standards EN 50121 and 50115 incorporate environmental elements such as vibration, EMC, and temperature. IT requirements for ITS include rugged devices, high availability, and wireless access.